Modal logic is usually treated as an extension of classical logic that allows us to reason formally about modes of truth, such as necessity and possibility. While classical propositional and predicate logic are concerned with what is the case, modal logic adds expressive resources to talk about what must be the case, what could be the case, what ought to be the case, what will be the case, and what is known or believed, etc. Because of this flexibility, modal logic has found applications in philosophy, linguistics, computer science, artificial intelligence, mathematics, and other fields. Typical modal notions include metaphysical necessity and possibility, epistemic notions such as knowledge and belief, deontic notions such as obligation and permission, and temporal notions concerning time. Modal logic provides a formal framework for analyzing these concepts, clarifying their logical structure and the relations between them. Modal logic can be understood in a wide or a narrow sense. In the wide sense, it includes temporal logic, deontic logic, epistemic logic, and related systems. In the narrow sense, it focuses on necessity, possibility, and closely related modes of truth. In this introduction, we concentrate on modal logic in the narrow sense. Other introductions will address temporal logic, deontic logic, and related logics. The most common modal operators are the box, read necessarily, and the diamond, read possibly. Intuitively, box A, or it is necessary that A means that A is true in all relevant alternatives, while diamond A, or it is possible that A means that A is true in at least one relevant alternative. These operators are interdefinable. Diamond A is equivalent to not box, not A, and box A is equivalent to not diamond, not A. Modal logic helps us formalize reasoning patterns such as, if something is necessary, then it is the case, or if something is the case, then it is possibly the case. Such patterns cannot be adequately captured by classical logic alone, which treats all truths as unqualified, at least not in a natural way. The syntax of propositional modal logic is built on top of classical propositional logic. Starting with propositional variables, logical connectives, such as not, and, or, etc., and parentheses, we add the modal operators, box and diamond. If A is a well-formed formula, then box A and diamond A are also well-formed formulas. More complex formulas are built recursively using the standard rules of formation. Modal formulas can be nested, allowing expressions such as box diamond A or diamond box A. The syntax itself does not fix the interpretation of the modal operators. This is done by the semantics. The most influential semantics for modal logic is possible worlds semantics. According to this approach, modal truth is evaluated relative to a set of possible worlds rather than a single world. A modal model consists of a non-empty set of possible worlds, an accessibility relation between worlds, a valuation function assigning truth values to propositional variables at each world, a formula box, A, or it is necessary that A is true at a world W if, and only if A is true at all worlds accessible from W. A formula diamond, A, or it is possible that A is true at W if and only if A is true in at least one world accessible from W. The accessibility relation encodes the intended modal interpretation, such as metaphysical possibility, epistemic alternatives, or moral ideals. Different modal systems arise by imposing different constraints on the accessibility relation. System K is the weakest so-called normal modal system. It places no restrictions on accessibility beyond what is required for the basic modal axioms. System T adds reflexivity. Every world is accessible from itself. This validates the principle, if it is necessary that A, then A. System B adds symmetry. If W accesses V, then V accesses W. This validates the principle, if A, then it is necessary that it is possible that A. System 4 adds transitivity. If W accesses V and V accesses U, then W accesses U. This validates the principle. If it is necessary that A, then it is necessary that it is necessary that A. System 5 combines reflexivity, symmetry, and transitivity, resulting in an equivalence relation. It is often used to model, for example, metaphysical necessity or idealized knowledge. Each system captures different intuitions about necessity and possibility. Several proof methods are used in modal logic. Hilbert-style axiom systems extend classical axioms with modal axioms and inference rules such as necessitation. Natural deduction systems adapt classical rules and add introduction and elimination rules for modal operators. Semantic tableaux are particularly popular. They test validity by attempting to construct a countermodel with possible worlds and accessibility relations. Sequent calculi and labeled deduction systems explicitly represent worlds and accessibility relations in proofs. Propositional modal logic treats propositions as basic units and does not quantify over individuals. Quantified modal logic combines modal logic with predicate logic, introducing quantifiers that range over individuals. This raises additional philosophical and technical issues, such as whether individuals exist in all possible worlds and how identity across worlds should be understood. Different choices lead to different semantic frameworks, such as constant domain and varying domain semantics. In modal logic, a sentence is logically true if and only if it is true at every world in every model. A sentence is logically false if and only if it is false at every world in every model. A sentence is logically contingent if and only if it is true in at least one world in some model and false in at least one world in some model. These notions generalize classical concepts but depend on the modal structure of models and accessibility relations. A formula B is a logical consequence of a set of formulas S, if and only if, in every model and every world. Whenever all formulas in S are true, B is also true. An argument is valid if and only if its conclusion is a logical consequence of its premises. As in classical logic, validity depends on form rather than content, but modal operators introduce additional structural constraints. Most standard propositional modal systems are sound and complete with respect to their semantics. Many are also decidable, unlike first-order logic. Quantified modal logic, however, often loses decidability and completeness under certain interpretations. Modal logic extends classical logic by providing formal tools to reason about necessity, possibility, and related notions. Through its rich syntax, possible world semantics, and diverse proof systems, it offers a powerful framework for philosophical and formal analysis. Despite its complexity, modal logic remains one of the most important developments in modern logic.